Good evening, and welcome to today's episode. If you're listening to this, you've probably come here to let your thoughts drift gently away from the day, to allow your breathing to settle into a quieter rhythm, to float peacefully through the cosmos as sleep finds you. You're in the right place. Tonight's journey takes us outward into the infinite darkness, where stars whisper ancient secrets and galaxies spiral in patient dance. Space holds 101 quiet facts, each one stranger and more beautiful than the last. What could the universe possibly want to tell us as we drift toward sleep? Now, before we float too far, I should mention that counting facts is perhaps the universe's gentlest lullaby. Before we begin, I'd love to know where in the world you're listening from. It always touches me to see these quiet journeys reach so many corners of the globe. If you enjoy these calm explorations, please give the video a like and subscribe to the channel. It really helps others find this peaceful corner of science. To those already subscribed, thank you. Your support means the world. Please also click the notification bell so you won't miss the next quiet adventure we take together. I do hope this video isn't too interesting that it keeps you awake. But if it does, at least you'll drift off having learned something quietly wonderful about the cosmos above us. So, settle in, relax, let your shoulders drop, and allow your mind to drift gently outward into the velvet darkness. Let's begin tonight's exploration. What space whisper to those patient enough to listen? Chapter 1. The nature of space. Let's drift into understanding what space actually is. Empty. Or so it seems. But emptiness itself is something rather profound. A canvas where everything we know floats and spins and quietly burns. Space is the stage, and we're just watching the performance unfold. Space, in its simplest form, is the vast expanse between celestial objects. It's mostly vacuum, mostly nothing, mostly quiet, but that mostly matters. Imagine ancient astronomers gazing upward from mountaintops and temples. They saw the same stars we see, the same patient moon, the same wandering planets. Those early observers believed space was filled with crystalline spheres, solid and eternal, carrying the heavens in perfect circles. It took centuries for us to realize that space wasn't solid at all. It was absence. It was room. It was possibility. There's something humbling about looking upward and realizing that the darkness between stars isn't just empty, it's where everything happens. Think of it like this silence between musical notes. Without that space, without that pause, there would be no melody, no rhythm, no song. Space is the universe's silence. And within that silence, galaxies compose their slow symphonies. Space begins about 100 kilometers above Earth's surface, at something called the Carmine Line. Below that, atmosphere. Above it, void. The transition is gentle, not sudden. Air molecules simply spread farther apart, drifting, thinning, until there's almost nothing left to breathe. Temperature loses, meaning that without air to carry heat, you could float simultaneously frozen and scorched to your body, radiating warmth into infinite cold, while the sun's unfiltered rays burn the side facing it. Space contains roughly 1 hydrogen atom per cubic centimeter. 1 atom in a space the size of a sugar cube. That's how empty really is. Yet even in that near-perfect vacuum, particles drift, radiation hums. Quantum fields shimmer with possibility. It's a bit like an ocean, only instead of water, it's filled with potential, with the ghost of matter, with invisible forces pulling and pushing in gentle waves. Scientists measure space in light years, parsecs, astronomical units, distances so vast they need to be translated into time. Light itself, the fastest thing we know, takes years to cross the gaps between stars. Think about that. The ultimate speed limit of the universe, and still space, makes even light seem slow and patient. Yet even with all we know, mysteries remain. Dark matter fills space with invisible presence. Dark energy pushes galaxies apart with quiet insistence. We float through something we barely understand, surrounded by forces we cannot see. So perhaps that's why space feels so profound. It challenges everything we think we know about presence and absence. We too exist in the spaces between atoms, in the gaps between heartbeats, in the pauses between thoughts. In that emptiness, we find room to wonder. It's a reminder that nothing is never truly nothing. Proof that the universe saves its deepest secrets for the quiet observers. Chapter 2. Stars and their patient burning. Let's drift into the realm of stars. Those ancient lanterns scattered across the cosmic dark. They burn. Quietly. Patiently. For billions upon billions of years, fusing hydrogen into helium in their cores while we spin beneath them, barely noticing their constancy. A star is a massive sphere of plasma, held together by its own gravity, simple enough. But within that simplicity hides extraordinary violence rendered gentle by distant nuclear fusion happening 1,000,000 times per second. Temperatures reaching 15 million degrees, pressures that would crush any earthly matter into oblivion. Ancient sailors, navigated by lovers, whispered beneath constellations. Philosophers pondered whether stars were holes poked through heaven's dome, or distant suns like ours. The truth turned out more beautiful than any myth. Each star is a sun. Each point of light potentially warming planets we'll never see. Perhaps casting shadows for beings who look up at their own night sky and wonder. Think of stars like candles burning in a vast cathedral, each one small, each one temporary, but together they illuminate the darkness with patient light. Not quite right. Of course candles burn for hours. Stars for eons, but the metaphor holds. They consume themselves to shine. Our sun is startlingly average. Medium-sized, middle-aged, yellow, unremarkable. Yet it's everything to us. It burns through 4 million tons of matter every single second, converting mass into energy through Einstein's famous equation. That energy takes thousands of years to work its way from the sun's core to its surface, bouncing between particles in a slow dance, before finally streaming outward at light speed to warm your face. 8 minutes and 20 seconds later, stars come in colors. Red giants glow like coals. Blue supergiants burn fierce and hot. White dwarfs fade into crystalline corpses. Brown dwarfs never quite manage to ignite at all. Failed stars drifting in the dark. The color tells you temperature. Blue burns hotter than white, white hotter than yellow, yellow hotter than red. It's backward from what we expect. But the universe often is. Picture a factory that runs for 10 billion years without stopping. That's a star. Raw materials go in hydrogen mostly, and energy comes out. Light, heat, heavier elements forged in stellar cores. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it cooked inside ancient stars that died before our sun was born. Betelgeuse, the red giant marking Orion's shoulder, has swollen to enormous size. If you placed it where our sun sits, its surface would extend past Mars. It's nearing the end of its life, ready to explode as a supernova sometime in the next 100,000 years. Could be tomorrow, could be in 1,000 centuries. When it does, the explosion will briefly outshine entire galaxies, visible in daylight from Earth, casting shadows at midnight. Yet for now, it simply glows, patient, waiting for its dramatic finale. Back in 1054, Chinese astronomers recorded a guest star appearing in the constellation Taurus. It shone bright enough to see during the day, remaining visible for months before fading. What they witnessed was a supernova star's death cry echoing across 1,000 light. The remnant still glows today, an expanding cloud of debris called the Crab Nebula, powered by a spinning neutron star at its heart that pulses 30 times per second, like a cosmic lighthouse. It's humbling to think that every element heavier than helium was forged inside stars. We are quite literally made of stardust, not metaphorically. Actually, the atoms comprising your body were assembled in stellar furnaces that burned and died before Earth existed. Most stars come in pairs or groups. Our sun is unusual, a loner drifting through space without a companion. Binary stars orbit each other in gravitational embrace, sometimes so close they share material between them, sometimes so distant they barely feel each other's pull. Triple star systems exist. Quadruple. The more stars in a system, the more complicated their cosmic dance becomes orbits within orbits. Gravitational choreography that would dizzy any mathematician. Imagine standing on a planet orbiting a binary star. 2 suns in your sky. 2 sunrises, 2 sets of shadows. Depending on the orbit, you might have periods with no night at all, or moments when both suns set simultaneously, plunging the world into unexpected darkness. Life there, if it exists, must have evolved very different circadian rhythms. Stars don't live forever. Small ones burn slowly, conserving their fuel, potentially glowing for trillions of years. Massive ones burn hot and fast, exhausting themselves in mere millions of years, cosmically speaking. A brief candle, the largest stars ever discovered, would fit our entire solar system inside them. The smallest barely qualify as stars at all. Red dwarfs dim enough that none are visible to our naked eyes, despite being our most common stellar neighbors. Perhaps there's something comforting about stars. They remind us that burning bright doesn't mean burning forever. That patience allows for longer journeys. That even the mightiest suns eventually fade into quiet darkness. We too burn our fuel, shine our light, and return to the cosmic dark from which we came. In that parallel, we find perspective. It's a reminder that impermanence doesn't diminish beauty, it enhances it. Proof that the universe measures time in scales that make our worries seem charmingly small. Chapter 3. Planets and their silent orbits. Now we turn to planets. Those wandering worlds that drift through darkness on invisible tracks. They orbit silently, endlessly, following paths determined billions of years ago when dust and gas collapsed into spinning disks around newborn stars. A planet is a celestial body that orbits a star, possesses enough mass for gravity to pull it into a roughly spherical shape, and has cleared its orbital neighborhood of debris. That last bit matters. It's why Pluto got reclassified as a dwarf planet, much to everyone's quiet dismay. Ancient observers called them wanderers, because they moved against the fixed stars. Mars, Jupiter, Saturn, Venus, Mercury. Visible to naked eyes, they traced slow paths across constellations, mysterious and divine. Different cultures saw different gods reflected in their movements, but all recognized something special about these lights that refused to stay still. Think of planets like dancers on an invisible stage. They move to music we cannot hear, following choreography written by gravity and momentum, each one at a different distance, a different speed, a different rhythm, not quite colliding, never quite syncing, but somehow maintaining perfect harmony. Our solar system contains 8 planets now, for rocky worlds close to the Sun: Mercury, Venus, Earth, Mars small and solid and warm, for gas giants farther out: Jupiter, Saturn, Uranus, Neptune massive and cold and surprisingly light for their size. Between them, an asteroid belt marks the boundary, a ring of debris that never quite coalesced into a planet, prevented by Jupiter's immense gravitational influence. Mercury orbits closest to the Sun, scorched and cratered and silent. Its day lasts longer than its year, a peculiar consequence of tidal locking and orbital resonance. One side bakes at 430 degrees Celsius, the other freezes at -180. There's no atmosphere to distribute the heat, no weather to soften the extremes, just rock and radiation, and the Sun looming enormous in a black sky. Venus glows brightest in our sky, beautiful from afar. Up close, it's hell. Atmospheric pressure 90 times Earth's. Surface temperature hot enough to melt clouds of sulfuric acid. Volcanoes that might still be active, yet billions of years ago, Venus might have had oceans, might have been temperate, might have been habitable. Something went wrong, runaway greenhouse effect, that boiled the seas and turned paradise into furnace. Picture Earth from space, that blue marble swirled with white clouds, brown continents, deep oceans. We're the only planet we know for certain that harbors life. Not just simple life, but complex ecosystems, consciousness, civilization. Whether that makes us common or cosmically lonely, remains the greatest question. For now, we spin in the habitable zone. Not too hot, not too cold, with liquid water and magnetic fields protecting us from solar radiation. Mars glows red with iron oxide rust. A desert world with polar ice caps and ancient river valleys carved when water flowed freely across its surface. Rovers trundle across its dunes, drilling rocks, analyzing soil, searching for signs that life once existed there. Perhaps it did. Perhaps microbial Martians thrived billions of years ago, when Mars was warmer, wetter, more hospitable. If so, they're long gone now, leaving only mysteries in the sand. Jupiter reigns as king of planets, more massive than all other planets combined. Its great red spot is a storm larger than Earth that's raged for centuries. Lightning flashes in its clouds. Auroras dance at its poles. It has at least 95 moons, some large enough to be planets themselves if they orbited the Sun directly. Europa hides an ocean beneath its ice. Io erupts with volcanic fury. Ganymede generates its own magnetic field. Back in 1610, Galileo pointed his telescope at Jupiter and saw 4 moons orbiting it. That simple observation shattered the idea that everything revolved around Earth. Here was proof celestial bodies orbiting something else. The universe suddenly became much larger, much less anthropocentric, much more wonderful. It's profound to realize Jupiter probably saved Earth from countless asteroid impacts. Its massive gravity acts as a cosmic vacuum cleaner, sweeping up debris that might otherwise plunge toward the inner solar system. Some scientists suggest complex life on Earth might never have evolved without Jupiter standing guard in the outer darkness. Saturn floats in space with those magnificent rings, billions of ice particles ranging from dust specks to house-sized boulders, all orbiting in elegant planes, so thin they nearly disappear when viewed. The rings might be temporary, cosmically speaking. They could be debris from a shattered moon or leftover material from the planet's formation. Either way, they'll eventually spiral into Saturn or disperse into space, giving us only a few 100 million years to admire their beauty. Imagine sailing through Saturn's rings in a spacecraft. Ice chunks would surround you, glittering in sunlight, each one on its own orbit, all moving together like a slow avalanche frozen in time. You could reach out and touch primordial ice, material unchanged since the solar system's birth. Uranus rolls on its side, probably knocked over by a massive collision billions of years ago. It rotates at a 90-degree angle to its orbit, giving it extreme seasons. Each pole experiences 42 years of continuous sunlight, followed by 42 years of total darkness. The planet glows blue-green from methane in its atmosphere, cold and distant and strange. Neptune churns with the fastest winds in the solar system's supersonic storms, racing across a world that receives 900 times less sunlight than Earth. It's so far from the Sun, it hasn't completed a full orbit since its discovery in 1846. Triton, its largest moon, orbits backward, suggesting it was captured from the Kuiper Belt rather than forming alongside the planet. Perhaps planets teach us about possibility. 8 worlds, 8 entirely different environments, 8 unique stories written by the same physical laws playing out under different conditions. We too are shaped by our circumstances, by gravity and chemistry and random chance. In that variety, we find wonder. It's a reminder that similar beginnings can lead to vastly different endings. Proof that the universe delights in variation. Chapter 4. Moons and their quiet companionship. From here, our journey takes us to moons, those faithful companions that orbit planets as planets orbit stars. They drift silently. Some large enough to be worlds themselves, others mere captured asteroids tumbling through space. Each one a reminder that companionship takes many forms. A moon is a natural satellite, a celestial body that orbits a planet or dwarf planet. Some planets have none, others have dozens. Jupiter and Saturn collect moons like cosmic hoarders, their gravitational influence capturing anything that wanders too close. Ancient peoples tracked our moon with reverence. It controlled tides, it marked time, it inspired calendars and myths and midnight poetry. Full moons lit hunting trails. New moons brought darkness for storytelling. The moon's phases became metaphors for cycles, for change, for the reliable return of light after darkness. Think of moons like children playing around a parent. They circle endlessly, held close by gravity's invisible hand. Each one different, each one finding its own stable orbit. Some close and fast, others distant and slow. Not quite independent, not quite bound, but comfortable in their eternal dance. Our moon, capital M, because it's ours, formed from a catastrophic collision. About 4.5 billion years ago, a Mars-sized object crashed into the young Earth. Debris splashed into orbit. That debris coalesced. What emerged was the moon, born from violence, but settling into patient companionship. Tidally locked so the same face always points toward us, hiding its far side until humans finally sent spacecraft to peek. The moon drifts away from Earth at about 4 centimeters per year. Slowly, imperceptibly. Tidal forces steal rotational energy from Earth and transfer it to the moon's orbit, nudging it outward. Billions of years ago, the moon loomed much larger in our sky, much closer, causing enormous tides that reshaped shore. Billions of years hence, it will appear smaller, weaker, eventually escaping Earth's gravity entirely. Picture the moon as it was in dinosaur times, closer, brighter, moving faster across the sky. Tides surged higher. Days passed quicker. The moon's pull helped stabilize Earth's axial tilt, preventing wild climate swings that might have made complex life impossible. Without the moon, Earth might wobble chaotically, seasons becoming unpredictable, weather turning hostile. Our steady companion keeps us level. Europa shines as one of Jupiter's most intriguing moons. Beneath its cracked ice surface lies an ocean liquid water, salty, warmed by tidal flexing as Jupiter's gravity squeezes and stretches the moon's interior. That ocean might harbor life, simple organisms thriving in darkness, feeding on chemical energy like creatures near Earth's deep-sea hydrothermal vents. We don't know yet, but the possibility whispers enticingly. Imagine diving beneath Europa's ice. Darkness above, darkness below. But in between, an ocean larger than all of Earth's combined, with potential for chemistry, for complexity, for biology. Somewhere in that alien sea, something might drift, might metabolize, might reproduce. Or perhaps it's sterile, empty, beautiful nonetheless. Io erupts continuously. It's the most volcanically active body in the solar system, covered with sulfur flows and lava lakes and towering plumes that shoot hundreds of kilometers into space. Jupiter and its other large moons pull at Io from different directions, generating tidal heating so intense the moon's interior stays molten. It's being slowly pulled apart by gravity, erupting constantly, reshaping itself with every passing orbit. Titan, Saturn's largest moon, hides beneath a thick orange haze. It's the only moon with a substantial atmosphere thicker than Earth's, actually. Lakes of liquid methane and ethane pool on its surface. Rivers of hydrocarbons flow through icy landscapes. Rain falls, but not water methane precipitation that carves river channels and fills hydrocarbon seas. It's a world of familiar processes happening with alien chemistry. Back in 2005, the Huygens probe descended through Titan's atmosphere, parachuting toward the surface while cameras captured the view. The images showed river networks, rounded pebbles, a shoreline. For all the alien chemistry, Titan looks strangely Earth-like geology without biology. Weather without life, a world that might show us what early Earth resembled before life emerged. It's remarkable how moons serve as laboratories for understanding planetary processes. Each one offers a different experimentio for volcanism. Europa for subsurface oceans, Titan for atmospheric dynamics. Enceladus for cryoval. Saturn's moon Enceladus shoots geysers of water ice into space from cracks near its south pole. Geysers that come from a subsurface ocean. Geysers that rain back down as snow. Triton orbits Neptune backward, the only large moon in the solar system, with a retrograde orbit. It's slowly spiraling inward, doomed to crash into Neptune, or be torn apart into rings within a few billion years. For now, it remains intact, covered with nitrogen ice, erupting with geysers of dark material that stained its surface with mysterious streaks. Picture Triton's sky Neptune, hanging enormous and blue, barely moving because Triton is tidally locked. The sun appears as just a bright star, distant and cold. Geysers erupt silently in near vacuum, spewing material that arcs hundreds of meters before settling back to the frozen surface. It's desolate, beautiful, temporary. Phobos and Deimos, Mars's two small moons, might be captured asteroids. They're lumpy, dark, cratered. Phobos orbits so close to Mars, it races around the planet 3 times per Martian day, rising in the west and setting in the east backward from how moons normally behave. It's also spiraling inward, destined to crash into Mars or break apart into rings within 50 million years. Perhaps moons teach us about relationship. They show us that orbiting something larger doesn't diminish pursuit, creates stability, generates energy through tidal forces, provides perspective on the parent world. We to orbit others in our lives, finding balance between independence and connection. In that orbital dance, we find meaning. It's a reminder that companionship shapes us, even when we don't realize it's happening. Proof that the universe builds complexity through partnership. Chapter 5. Galaxies and their spiral patience. Let's drift into the realm of galaxies. Those cosmic cities where billions of stars cluster together in gravitational embrace. They spiral, slowly, majestically, taking hundreds of millions of years to complete a single rotation, so patient that even stars seem rushed by comparison. A galaxy is a massive collection of stars, gas, dust, and dark matter bound together by gravity. They come in shape spirals like ours, ellipticals like cosmic eggs, irregulars that defy easy description. Each galaxy containing hundreds of billions of stars, each star potentially hosting planets, each planet perhaps harboring life. Ancient astronomers saw fuzzy patches in the night sky and called them nebulae, Latin for clouds. They had no idea these smudges were actually distant galaxies' entire separate collections of stars so far away. Their light merged into indistinct glows. It was until the 1920s that Edwin Hubble proved these nebulae existed far beyond our own Milky Way, expanding our cosmic address from one galaxy among, well, we're still counting. Think of galaxies like cities seen from an airplane at night. From far away, they glow as single points of light. Draw closer and individual structures emerge as spiral arms, bulges, halos. Closer still and individual stars resolve, each one a distinct light, each one orbiting the galactic center in patient procession. Not quite cities, but the metaphor holds concentrated density, surrounded by emptiness. Our Milky Way stretches about 100,000 light-years across. We live in a spiral arm called the Orion Spur, about halfway out from the galactic center, orbiting at roughly 828,000 kilometers per hour. At that speed, we complete one galactic orbit every 225 million years. Dinosaurs last walked Earth one galactic rotation ago. The Sun has orbited perhaps 20 times since forming. The Milky Way center hides a supermassive black hole called Sagittarius A*, pronounced as. It contains 4 million times the Sun's mass, compressed into a region smaller than Mercury's orbit. Stars near it move so fast their orbits trace out in human lifetimes, some completing full elliptical paths in just decades, screaming around the black hole at substantial fractions of light speed. Picture standing near the galactic center. The night sky would blaze with stars packed so densely they merge into continuous glow. No darkness between them, no constellations, just overwhelming light in every direction, shadows cast by multiple stars simultaneously, a sky bright enough to read by even in the dead of night. Andromeda drifts toward us. It's our nearest large galactic neighbor, about 2.5 million light-years away, visible to naked eyes as a faint smudge in autumn skies. It contains roughly 1 trillion stars, more than twice the Milky Way's population, and it's approaching at about 110 kilometers per second, pulled by mutual gravitational attraction. In about 4 billion years, our galaxies will collide. But collide isn't quite right. Galaxies are mostly empty space. When they merge, stars will pass each other like ghosts, rarely coming close enough to interact directly. Instead, gravity will reshape both galaxies, flinging stars into new orbit, triggering waves of star formation as gas clouds compress, eventually creating a single elliptical galaxy from two spirals. The process will take billions of years, a slow-motion collision that unfolds across Back in 1995, astronomers pointed the Hubble Space Telescope at a tiny, apparently empty patch of sky and left the shutter open for days. What emerged became known as the Hubble Deep Field, nearly 3,000 galaxies in that one small region, each one containing billions of stars, most so distant their light had traveled for billions of years to reach us. Every patch of seemingly empty sky contains similar richness. The universe teems with galaxies. It's humbling to calculate the numbers. At least 200 billion galaxies in the observable universe. Perhaps more, each containing hundreds of billions of stars. The total number of stars exceeds the number of grains of sand on all Earth's beaches. And that's just what we can see. Limited by light speed and cosmic expansion, trapped by horizons we cannot cross. Elliptical galaxies look like cosmic eggs or footballs, containing mostly old red stars in random orbits rather than organized disk structures. They form through galaxy merges when spirals collide. Their organized structures get scrambled, leaving elliptical shapes. There, the universe's elderly population, past their star-forming prime, coasting towards slow fade. Imagined living in an elliptical galaxy. No grand spiral arms, no organized disk, stars orbiting in every direction. Some plunging through the galactic core, others wandering far into the halo. The night sky would show less structure, less pattern, just stars scattered seemingly at random, beautiful in its chaos. Irregular galaxies defy classification. They're lumpy, chaotic, often small. The large and small Magellanic Clouds visible from Earth's southern hemisphere are irregular galaxies, satellite galaxies, orbiting the Milky Way, close enough that our gravity distorts them, pulls at them, slowly consumes them through tidal stripping. Galaxy clusters group galaxies together through gravity. The Virgo cluster contains over 1,000 galaxies. The Coma cluster contains thousands more. These clusters form the large-scale structure of the universe filaments and walls of galaxies surrounding enormous voids, like cosmic foam, like the structure of soap bubbles, like three-dimensional spider webs, spanning billions of light. Perhaps galaxies teach us about community. Individual stars might shine briefly, but gathered together they create structures that persist for cosmic eternities. We to find strength in numbers, in belonging to something larger than ourselves. In that congregation, we find purpose. It's a reminder that isolation might be beautiful, but connection builds galaxies. Proof that the universe favors structures over solitude. Chapter 6. Black holes and their quiet hunger. Now we turn to black holes, those cosmic enigmas that swallow everything, including light itself. They pull, silently, eternally, warping space-time around them into inescapable wells from which nothing returns, where the normal rules break down, and physics itself seems to whisper, "Here be dragons." A black hole is a region of space-time where gravity has grown so strong that nothing, not matter, not light, not information can escape once it crosses the event horizon. They form when massive stars collapse, when matter compresses to infinite density, when space-time curves back on itself completely. Ancient philosophers never imagined such things. How could they? The idea that mass could warp space, that light could be trapped, that time itself would slow near extreme gravity, these concepts required Einstein's relativity, quantum mechanics, observations that could only be made with modern telescopes. Black holes remained theoretical until recently. Think of black holes like drains in space-time. Water near a drain spirals inward, accelerating, eventually vanishing down the hole. Not quite accurate. Space-time isn't a fluid, but the metaphor captures the inevitability, the one-way journey, the point of no return. Stellar black holes form from dead stars. When massive stars exhaust their nuclear fuel, nothing remains to hold them up against gravity's crush. the core collapses. Protons and electrons merge into neutrons. If the core exceeds about 3 solar masses, not even neutron degeneracy pressure can resist. Collapse continues. The star becomes a black hole, an object so dense its escape velocity exceeds light speed. The event horizon marks the boundary. Outside it, escape remains possible with enough speed. Inside it, all paths lead inward. Even light cannot climb back out. Even time behaves strangely. An observer falling toward the horizon would never see themselves cross it, frozen at the boundary from the perspective of outside observers, yet from their own perspective, they'd pass through smoothly, falling toward the central singularity where physics admits it no longer understands what happens. Picture approaching a black hole. First, you'd notice stars behind it, appearing distorted, their light bent around the black hole's mass. Draw closer, and the distortion intensifies the black hole, acting as a gravitational lens, creating multiple images of background stars, perhaps even showing you the back of your own head, if light managed to orbit before escaping. Closer still, and tidal forces would stretch you, pulling harder on your feet than your head if you fell feet first. A process charmingly called supermassive black holes lurk at galactic centers. They contain millions to billions of solar masses, far larger than stellar black holes, perhaps forming through different processes: direct collapse of massive gas clouds, mergers of smaller black holes, feeding on surrounding matter for billions of years. Nearly every large galaxy has one. They regulate star formation, influence galactic evolution, grow alongside their host galaxies in ways we're still working to understand. Sagittarius A, the supermassive black hole at our galaxy's heart, contains about 4 million solar masses. Scientists discovered it by tracking stars orbiting the galactic center. Stars moving so fast they must be orbiting something invisible and massive. One star, designated S2, completes its orbit in just 16 years, reaching speeds of 7,650 kilometers per second at closest approach. The orbit would fit inside Saturn's orbit around our Sun. Back in 2019, the Event Horizon Telescope captured the first image of a black hole. Actually, the glowing accretion disk surrounding the event horizon of M87's supermassive black hole, 55 million light-years away. The image showed a bright ring of material orbiting the black hole, with a dark shadow at the center where light couldn't escape. That shadow was cast by the event horizon itself, gravity made visible by its absence of light. It's profound to see something that by definition shouldn't be visible. We and photograph the black hole itself. It emits no light, but we can image the effects it has on surrounding material. The gravitational lensing, the radiation from matter spiraling inward and heating to billions of degrees before vanishing forever. Black holes aren't cosmic vacuum cleaners. They don't suck more than any object of equivalent mass. If you replaced the Sun with a black hole of equal mass, Earth would continue orbiting normally. No change in gravity, no inward spiral, just sudden darkness. The danger comes only if you approach too close, entering regions where tidal forces become destructive. Imagine a binary system with one normal star and one black hole. The black hole steals material from its companion. That material forms an accretion disk, spiraling inward, heating through friction, emitting X-rays bright enough to detect from Earth. Some binaries show regular pulses. Companion star passes in front of the black hole from our perspective. Sinus X1 was the first confirmed stellar black hole, discovered through exactly such observations. Hawking radiation suggests black holes aren't entirely black. Quantum effects near the event horizon allow particle-antiparticle pairs to form. Occasionally one particle falls in while the other escapes, appearing as radiation from the black hole's perspective. The process is incredibly slow for large black holes. A solar mass black hole would take 1,067 years to evaporate through Hawking radiation, far longer than the current age of the universe. But eventually, even black holes must fade. Perhaps black holes teach us about finality. They represent the ultimate end state for massive stars. Gravity's final victory. The universe taking matter and compressing it to mathematical abstraction. Yet even in that absolute ending, new physics emerges. New questions arise. New mysteries wait to be explored. We too face endings, transformations, points of no return. In that inevitability, we find perspective. It's a reminder that even the universe's darkest phenomena still teach us about light. Proof that mystery remains even in things we cannot see. Chapter 7. Nebulae and their colorful whispers. Let's drift into nebulae. Those cosmic clouds where stars are born and where stars return their enriched material after death. They glow softly, painting space with colors reds and blues and greens, while hydrogen and helium and heavier elements drift together in patient assembly. A nebula is an interstellar cloud of dust, hydrogen, helium, and ionized gases. The word means cloud in Latin, and that's exactly what they look like. Cosmic clouds illuminated by nearby stars, glowing with their own light, or backlit by stars behind them, or dark patches blocking the light beyond. Ancient astronomers cataloged these fuzzy objects without understanding their nature. Charles Messier, an 18th century comet hunter, grew frustrated finding cloudy objects that weren't comets. He compiled a list of Messier cataloged, describing their locations so he and others could avoid confusion. Those annoying objects turned out to be some of the most beautiful structures in the universe. Think of nebulae like cosmic nurseries and graveyards combined. There, where stellar life begins and where it ends. Material cycling through stars and back to clouds, enriching the cosmos with each generation. Not quite birth and death, those words carry too much weight, but transformation. Continuity, the universe recycling its substance. The Orion Nebula glows bright enough to see with naked eyes on winter nights, a fuzzy patch in Orion's sword. It's a stellar nursery, a region where new stars form from collapsing clouds of gas. About 1,350 light-years distant, about 24 light-years across. Young stars within it are less than 1,000,000 years old, still gathering material, still igniting fusion, still establishing their eventual stable burning. Inside Orion, the trapezium cluster contains 4 bright stars, visible through small telescopes. Their ultraviolet radiation illuminates the surrounding gas, making it glow. These massive young stars will live only a few million years before exhausting their fuel and dying in supernova explosions that might trigger the next generation of star formation in surrounding material. Picture flying through a nebula. It wouldn't look like photographs suggest. Those images capture light accumulated over hours or days of exposure. To your eyes, the cloud would appear nearly transparent, faint wisps of gas barely visible. Density so low it approaches vacuum by Earth standards. Yet gravity works patiently, pulling gas together, concentrating it, collapsing it, until fusion ignites. Planetary nebulae have nothing to do with planets. William Herschel named them because through his telescope they looked like planetary disks. Actually, they're shells of gas expelled by dying stars, red giants shedding their outer layers, leaving behind hot cores that eventually cool into white dwarfs. The Ring Nebula in Lyra exemplifies this type. A perfect smoke ring, expanding slowly through space, illuminated by the dying star at its center. The Helix Nebula, nicknamed the Eye of God, shows us our sun's eventual fate. In about 5 billion years, the sun will swell into a red giant, consuming Mercury and Venus, possibly Earth, shedding its outer layers into space. What remains of the core will shrink into a white dwarf, and the expelled material will form a planetary nebula that might be visible from other star systems, glowing for perhaps 50,000 years before dispersing. Back in the 1990s, Hubble Space Telescope revealed extraordinary structures inside planetary nebula jets and bubbles and complex geometries that astronomers are still working to explain. Some planetary nebulae look like butterflies, others resemble hourglasses. Still others show multiple shells, suggesting multiple episodes of mass loss. Each dying star creates unique patterns, painting its final portrait across light. It's beautiful how death enriches the cosmos. Stars forge heavy elements in their cores: carbon, nitrogen, oxygen. Iron then return those elements to space when they die. Those elements become raw materials for the next generation of stars and planets. The atoms in your body were assembled inside dying stars billions of years ago, expelled in planetary nebulae or supernova, drifting through space until gravity gathered them into our solar system. Supernova remnants expand faster and more violently than planetary nebulae. When massive stars explode, they blast material outward at substantial fractions of light speed, creating shock waves that compress surrounding gas and trigger new star formation. The Crab Nebula expands at 1,500 kilometers per second, still growing almost 1,000 years after Chinese astronomers witnessed its parent star's death. Imagine the scale of a supernova remnant. The Crab Nebula spans about 10 light-years, now roughly twice the distance from the Sun to our nearest star, Proxima Centauri. And it's still expanding. At its center, a neutron star, pulsar, spins 30 times per second, powering the nebula's glow with beams of radiation sweeping across space like a cosmic lighthouse. Dark nebulae don't glow. They're dense enough to block light from stars behind them. The Horsehead Nebula, in Orion, appears as a dark silhouette against brighter background emission. The Coal Sack, near the Southern Cross, looks like a hole punched through the Milky Way. These dark clouds contain the densest material in the galaxy, perfect conditions for star formation, though we can't see the process happening inside. Reflection nebulae shine by reflecting starlight off dust grains. The Pleiades star cluster is surrounded by a blue reflection nebulodust, left over from the cloud that formed the cluster, now illuminated by the cluster's hot blue stars. Blue light scatters more easily than red, creating the characteristic color, the same physics that makes Earth's sky blue. Perhaps nebulae teach us about renewal. They show us that endings create beginnings, that material dispersed becomes material recollected, that the universe wastes nothing. We too scatter and gather, ending one chapter to begin another. In that transformation, we find continuity. It's a reminder that nothing truly disappears, it only changes form. Proof that the cosmos maintains perfect balance between creation and dissolution. Chapter 8. Asteroids and their ancient drift from here. Our journey takes us to asteroids, those rocky wanderers that drift between planets. Remnants from the solar system's formation, ancient time capsules preserving material unchanged for billions of years. They tumble silently, following elliptical paths that sometimes bring them near Earth, reminding us that space isn't empty, it's filled with debris. An asteroid is a minor planet, a rocky body, too small to be called a planet, composed mainly of metals and minerals. Irregularly shaped because their gravity isn't strong enough to pull them into spheres. Most orbit between Mars and Jupiter in the main asteroid belt, though some wander elsewhere. Ancient peoples occasionally witness fireballs, meteors, bright enough to cast shadows, sometimes leaving meteorites behind. They interpreted these sky stones as gifts from gods or omens of disaster. They had no framework for understanding that rocks could fall from space, that the heavens contained debris, that Earth moved through a shooting gallery of ancient stone. Think of asteroids like construction debris, left over after building a house. When the solar system formed from a rotating disk of gas and dust, most material clumped into the Sun and planets, but between Mars and Jupiter, conditions weren't quite right for a planet to form. Jupiter's gravity stirred things up, preventing coalescence, leaving behind millions of rocky fragments, each one a failed planet, each one preserving primordial material. The asteroid belt contains perhaps 2 million asteroids larger than a kilometer across, countless smaller ones down to dust particles. Yet despite this abundance, the belt is mostly empty space. If you flew through it, you'd likely never see another asteroid with your naked eyes. Movies depicting dense fields of tumbling rocks. Pure fiction. Reality is quieter, lonelier, more spread out. Ceres reigns as the asteroid belt's largest member, technically classified as a dwarf planet now because it's massive enough to pull itself into a sphere, about 950 kilometers in diameter. Perhaps containing a subsurface ocean, possibly still geologically active with ice volcanism. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, mapping mysterious bright spots that might be salt deposits left by sublimating ice. Picture standing on Ceres. Gravity would be with you. could jump several meters high. The sun would appear 3 times smaller than from Earth, but still bright enough to cast sharp shadows. The horizon would curve more noticeably because Ceres is so small. And above you, a black sky filled with stars that never twinkle because there's no atmosphere to distort their light. Near-Earth asteroids cross Earth's orbit or come close to it. Some are large enough that impact would cause global catastrophe. Asteroid 99942. Apophis will pass extremely close to Earth in 2029, enough that it will be visible to naked eyes as a bright point moving across the sky, closer than some satellites, within the region where communications satellites orbit. It won't hit us that time, but its orbit will be altered by Earth's gravity, making future predictions more complex. Back in 2013, a 20-meter asteroid exploded over Chelyabinsk, Russia, releasing energy equivalent to about 500 kilotons of TN, to roughly 30 times the Hiroshima bomb. The shock wave damaged buildings and injured over 1,600 people, mostly from shattered glass. Nobody saw it coming. It approached from the direction of the sun, invisible against the glare. The event reminded us that space rocks remain a genuine hazard. It's sobering to consider extinction events. About 66 million years ago, a 10-kilometer asteroid struck near what's now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear weapons, vaporizing rock, ejecting debris into orbit, triggering global firestorms. Dust and soot blocked sunlight for years. Photosynthesis collapsed. Food chains disintegrated. Roughly 75% of all species went extinct, including non-avian dinosaurs. Life persisted, but the world that emerged was fundamentally different. Asteroid mining remains mostly theoretical, but increasingly plausible. Some asteroids contain valuable metals: iron, nickel, platinum, gold concentrated during the solar system's formation. A single metallic asteroid might contain more platinum than has ever been mined on Earth. The challenges are immense. Reaching asteroids, extracting material in microgravity, returning it economically, but the resources available exceed anything terrestrial. Imagine establishing a mining base on a metallic asteroid. You'd anchor your equipment to the surface, because gravity barely exists. Mining would involve drilling or heating material until it melts. You might use magnetic separation, since many metals are magnetic. They wouldn't need processing to remove oxygen from minerals. Asteroids contain pure metal, already refined by the conditions in the early solar system. Trojan asteroids share a planet's orbit, sitting at stable gravitational points, called Lagrange points. Jupiter has thousands of Trojans, one swarm preceding Jupiter in its orbit, another following behind. Even Earth has at least one Trojan asteroid that we've discovered so far. These stable points act as cosmic harbors, where asteroids can persist indefinitely without being ejected by gravitational pull. Vesta shows features usually seen only on planets. It has a differentiated interior on iron core, rocky mantle, basaltic crusts, suggesting it was on its way to becoming a planet before Jupiter's gravity disrupted its growth. Ancient lava flows scar its surface. A massive impact crater dominates the southern hemisphere, so large the collision nearly shattered Vesta entirely. Some meteorites found on Earth came from that impact, ejected from Vesta millions of years ago. Perhaps asteroids teach us about preservation. They're time capsules, holding material unchanged since the solar system's birth. Samples of the primordial disk, messages from a time before planets fully formed. We too carry remnants of our origins, memories, and genes, passed down through generations. In those ancient remnants, we find connection to the past. It's a reminder that not everything changes. Some things persist across unimaginable time, proof that the universe keeps careful records. Chapter 9. Comets and their icy journeys. Now we turn to comets. Those icy wanderers from the outer darkness, visitors from the solar system's edge who occasionally swing close to the sun, warming and outgassing, growing magnificent tails that stream for millions of kilometers. They glow, briefly, brilliantly, then fade back into the cold from which they came. A comet is a small icy body that, when passing close to the sun, warms and releases gases, a process called outgassing that creates a visible atmosphere called a coma and sometimes tails. They're basically dirty snowballs, mixtures of ice, rock, and organic compounds left over from the solar system's formation, preserved in deep freeze until gravity brings them sunward. Ancient civilizations feared comets as omens. Their unpredictable appearances, their brilliant tails, their motion against the fixed starzole suggested divine messages or impending disaster. Comets announced births of kings and falls of empires. They appeared in historical records, in artwork, in prophecy. Only in recent centuries did we understand that comets follow predictable orbits, that they're natural objects governed by the same physics as planets. Think of comets like cosmic travelers on elliptical journeys. Most spend centuries or millennia in the dark outer solar system, frozen, solid, inactive. Then gravity nudges them sunward. They warm, ice sublimes. Pressure builds, gas and dust erupt, creating the coma and tails that make comets spectacular. Not quite meteorzos, are small and burn up in atmospheres, but something grander, more patient, more deliberate. Halley's Comet returns every 75 to 76 years. One of the few comets visible to naked eyes whose period is short enough for humans to witness multiple returns. Edmund Halley realized in 1705 that comet sightings from 1531, 1607, and 1682 described the same object on a periodic orbit. He predicted its return in 1758. It arrived on schedule, though Halley had died by then. The comet last appeared in 1986 and will return in 2061. The nucleus of a comet is surprisingly small, typically a few kilometers across, sometimes just hundreds of meters. But when warmed by the sun, that tiny nucleus can produce a coma hundreds of thousands of kilometers wide and tails stretching for tens of millions of kilometers. The tail always points away from the sun, not behind the comet's motion, pushed outward by solar wind and radiation pressure. Picture a comet approaching the sun, initially just a dark frozen lump tumbling through space. As sunlight strengthens, surface ice begins subliming, going directly from solid to gas without melting. Jets erupt from the nucleus, creating the coma. Two tails form a dust tail, curved and yellowish, following the comet's orbital path, and an ion tail, straight and bluish, pointing directly away from the sun. Sometimes, Earth passes through debris left by causing meteor showers, Perseids from comet Swift-Tuttle, Leonids from comet the Uart. Cloud surrounds our solar system like a spherical shell, extending perhaps a light year from the sun, roughly a quarter of the distance, to Proxima Centauri. Trillions of icy bodies orbit there, remnants from planetary formation flung outward by gravitational interactions with the giant planets. Occasionally passing stars or galactic tidal forces nudge an Earth cloud object sunward, sending it on a journey inward that might take millions of years. Back in 2014, the Rosetta spacecraft rendezvoused with Comet 67P. It orbited the comet for 2 years, watching it warm as it approached the sun, observing outgassing, studying the surface. Rosetta even deployed a lander, Philae, which bounced across the surface in the weak gravity before settling into a shadowed region. The mission revealed a world stranger than expected: a rubber duck-shaped nucleus, cliffs and plains, regions of different activity, layers of dust over ice. It's humbling how comets delivered volatiles to Earth. Early Earth was hot, baked dry by the sun, lacking the water and organic compounds needed for life. Comets bombarded the young planet, bringing ice that melted into oceans and carbon compounds that might have seeded prebiotic chemistry. We might owe our existence to these icy visitors, to billions of comet impacts 4 billion years ago. Some comets don't survive their close approach to the sun. Sungrazer comets plunge so close to the solar surface they evaporate entirely, disintegrating in the intense heat and tidal forces. Cameras on solar observatories regularly capture comets making their final death plunge, brightening briefly before vanishing forever into the sun's glare. Imagine riding a comet nucleus. You'd barely feel gravity jump in would send you floating away unless you held on. The surface would be dark, almost black, covered with organic compounds baked by previous sun passage. As you approached the sun, the surface beneath you would begin venting jets of gas and dust. The coma would envelop you, particles streaming past, tails forming from material that was solid hours earlier. Temperature would rise, ice would sublime. The nucleus would lose mass with each orbit, slowly wearing away. Short-period comets orbit in decades or centuries, originating from the Kuiper belt beyond Neptune. Long-period comets might take thousands or millions of years to orbit, coming from the Oort cloud, sometimes making a single pass before being ejected from the solar system entirely. Comet Neowise, visible to naked eyes in 2020, won't return for nearly 7,000 years. Most people who saw it were witnessing something nobody would see again for 70 centuries. Perhaps comets teach us about cycles and journeys. They show us that even objects flung into darkness eventually return, that ellipses bring wanderers home, that patience spans timescales beyond comprehension. We too journey outward into unknown darkness, and, if we're fortunate, find our way back to warmth. In that return, we find completion. It's a reminder that the universe operates on cycles we can barely perceive. Proof that even the longest journeys eventually reach their destinations. Chapter 10. Deep Dive. The cosmic microwave background. Let's drift deeper into perhaps the universe's most profound ikutha, cosmic microwave background radiation. This faint glow permeates all of space, a fossil record of the universe's infancy. Light from the earliest moment when the cosmos became transparent, it whispers to us across 13.8 billion years, carrying information about what the universe was like when it was just 380,000 years old. Picture the very early universe, unimaginably hot, unimaginably dense. Matter and energy so concentrated that atoms couldn't form electrons and nuclei stayed separate, creating a plasma so opaque that light couldn't travel freely. Photons scattered off free electrons constantly, trapped in cosmic fog, unable to move far before interacting again. Then the universe expanded and cooled. Temperature dropped below about 3,000 degrees Celsius. Suddenly, electrons and nuclei could combine, forming the first neutral hydrogen atoms. This process, called recombination, made the universe transparent. Light could finally travel freely. Photons that had been trapped were released, streaming outward in all directions, carrying the imprint of that moment. That light still travels today. We call it the cosmic microwave background, or CMB. As the universe expanded, the light stretched, shifting from visible light to infrared to microwaves, electromagnetic radiation with wavelengths measured in millimeters. It's everywhere. It fills all of space. Point a specialized detector in any direction and you'll detect it. A uniform glow at about 2.7 degrees above absolute zero. Think of the CMB like cosmic baby pictures. It shows us what the universe looked like in its infancy, before stars formed, before galaxies assembled, before complexity emerged. Not quite photographs, more like temperature maps, but invaluable for understanding cosmic origins. Imagine tuning an old analog television to static between channels. About 1% of that static comes from the CMB-XL cosmic radiation pervading the universe. Visible, even on consumer electronics, you're seeing light from the beginning of time, right there in the noise. It's a bit like finding ancient messages hidden in television snow. Only these messages tell the story of existence itself. The CMB isn't perfectly uniform. Tiny temperature fluctuations exist, regions that were slightly hotter or cooler by about 1 part in 100,000. These fluctuations are incredibly important. They represent quantum variations amplified during cosmic inflation, density variations that would eventually grow into galaxies, clusters, and the large-scale structure we observe today. Scientists mapped these fluctuations using spacecraft like COBE, WMAP, and Planck. The resulting images show the entire sky colored by temperature-red regions slightly warmer, blue regions slightly cooler. The patterns match theoretical predictions remarkably well, confirming our understanding of cosmic evil. Testing models of inflation, measuring fundamental parameters, like the universe's age, composition, and geometry. It's profound how much information hides in those subtle temperature variations. From CMB measurements, we've determined that the universe is 13.8 billion years old, that it's geometrically flat, that it contains about 5% ordinary matter, 27% dark matter, and 68% dark energy. All this from analyzing faint microwave glow. The CMB reveals that the universe underwent exponential expansion called cosmic inflation in its first fraction of a second. This inflation stretched quantum fluctuations to cosmic scales, creating the seed patterns we observe in the CMB, patterns that would eventually collapse under gravity to form structures. Without inflation, the universe would be too smooth. Two uniform galaxies wouldn't exist. Stars wouldn't form, we wouldn't be here. Consider the acoustic oscillations imprinted in the CMB. Before photons and matter were coupled together, creating pressure wave sound waves rippling through the primordial plasma. These waves froze when recombination occurred, leaving a characteristic pattern of alternating compressions and rarefaction. We can detect this pattern, measure the sizes of these acoustic peaks, and use them to determine cosmic parameters with extraordinary precision. Perhaps one day we'll detect gravitational waves from the CMB, patterns created by gravitational waves from inflation. Such detection would provide direct evidence for quantum gravity effects, opening a window to physics at energy scales we could never reach with particle accelerators. Several experiments are searching for this signature, looking for swirls in the CMB polarization that would indicate primordial gravitational waves, so the cosmic microwave background is really about evidence. It's the smoking gun for the Big Bang, confirmation that the universe had a beginning, proof that space itself expands, validation of our cosmological models. It connects us directly to the universe's earliest moments, allowing us to study conditions no experiment could recreate. In that ancient light, we find our origins. It's a reminder that even the most distant past leaves traces, whispers, that persist across cosmic time. Proof that the universe keeps records of everything that ever happened. Chapter 11. Philosophy of space beyond the facts and figures, beyond the measurements and observations. What does space teach us about existence itself? What wisdom hides in the darkness between stars? What meaning can we extract from distances too vast to truly comprehend? Space reminds us of scale. Our planet is tiny. Our sun is average. Our galaxy is one among hundreds of billions. And yet, on this insignificant rock orbiting an unremarkable star in the suburbs of an ordinary galaxy, consciousness emerged. Minds capable of understanding their cosmic context, of measuring distances to other galaxies, of contemplating the universe's origin and fate. That's remarkable. Perhaps the universe became conscious through us, aware of itself through our eyes, thinking about itself through our minds. There's something profound about that realization. We are not separate from the cosmos. We are the cosmos examining itself. Every atom in your body was forged in stellar furnaces. You are literally made of star material. When you look at the night sky, it's the universe looking at itself, recognizing itself, wondering about itself. This perspective collapses the artificial boundary between observer and observed, between self and universe. Perhaps space also teaches humility. Our concerns, our dramas, our urgent worries. Significant are they really, when measured against cosmic scales? The universe operates on timescales of billions of years. Our entire civilization's history spans perhaps 10,000 years. A cosmic eye. This isn't to diminish human concerns, they matter to us, which makes them matter, but perspective helps. Space reminds us that urgency is often it's like realizing you're a single cell in an impossibly vast organism. You matter to nearby cells, to the local tissue, to the organ you comprise. But zoom out far enough, and you're part of something incomprehensibly larger. Something that continues regardless of whether any individual cell survives. That can feel either terrifying or liberating, depending on your perspective. Yet space also demonstrates connection. Every particle in the universe shares a common origin. The Big Bang created everything from the same initial conditions. Cosmic inflation stretched quantum fluctuations into the density variations that became galaxies. Stars forged heavy elements and scattered them through space. Gravity gathered that enriched material into new stars, planets, eventually us. We are connected to everything through chains of causation, stretching back to the universe's beginning. Space shows us that isolation is an illusion. Light from distant stars reaches us, carrying information across billions of years. Gravitational waves from colliding black holes ripple through space-time, causing every particle in your body to shift. The sun's neutrinos stream through you every second. Cosmic rays from supernova strike your cells. We exist embedded in a web of interaction, constantly exchanging particles and energy with the cosmos around us. Perhaps the lesson is that meaning exists at multiple scales simultaneously. An electron matters to the atom it orbits. That atom matters to the molecule it forms. That molecule matters to the cell it builds. That cell matters to the organism it comprises. That organism matters to the ecosystem it inhabits. That ecosystem matters to the planet it shapes. That planet matters to the star it orbits. That star matters to the galaxy it inhabits. And that galaxy participates in the large-scale structure of the universe. You exist at all these scales at once. Your significance doesn't diminish at larger scales, it simply changes form. The atoms that comprise you will continue after you, becoming part of other structures, other systems, other expressions of matter and energy. Death isn't ending its transformation, recycling, continuation in different form. In the end, what space really teaches us is perspective. It shows us that the universe is vast beyond comprehension yet governed by understandable laws. It demonstrates that complexity emerges from simplicity, that order arises from chaos, that consciousness can emerge from unconscious matter following physical principles. We are the universe made conscious, studying itself, wondering about itself, finding meaning in its own existence. That might be the most profound fact of all. Closing. So here we are at the quiet end of our drift through space. 101 facts, though we barely scratched the surface of what the cosmos has to teach. Each fact, a window. Each window opening onto deeper mysteries. We've floated through the nature of space itself, through stars burning their patient fuel, through planets in silent orbit, through moons keeping faithful companion. We've drifted past galaxies spiraling across cosmic time, past black holes bending space-time, through nebulae where stars are born and die, through asteroids preserving ancient material, through comets on their elliptical journeys, and finally to the cosmic microwave background echoing from the universe's beginning, from vacuum to visible light, from quantum fluctuations to galactic superclusters. We've seen that the universe operates on principles both simple and profound. Gravity pulls, light travels. Matter transforms. Energy conserves. And within these simple rules, extraordinary complexity emerges: stars, planets, galaxies, consciousness, you. Perhaps what matters isn't memorizing facts, but recognizing patterns. Space shows us that the universe reuses the same principles at every scale. Atoms orbit nuclei like planets orbit stars. Galaxies cluster like molecules. Bond, the same physics that governs hydrogen in a test tube governs the sun's core. Understanding one helps us understand all. Because the cosmos plays fair, the rules do you want to change, just because we're re-looking at something vastly larger or infinitely smaller. Space reminds us that we're temporary. Our sun will fade. Our galaxy will merge with Andromeda. The universe itself will continue cooling and expanding until, in the unimaginably distant future, the last stars burn out and everything settles into quiet equilibrium. But that ending takes trillions of years. For now, for this cosmic moment, the universe is alive with starlight and planet forming, and perhaps even other consciousness, wondering about their place in the cosmos. Somewhere out there, photons continue their journey from the surface of distant stars, traveling through empty space at light speed, carrying information about stellar processes happening light years away. Some of those photons might reach Earth tonight. A few might enter your eyes if you look upward. Light from the past, arriving in the present, connecting you to stars that might already be dead, their light still traveling long after they cease to exist. That's perhaps the most beautiful thing about space. It connects us across time. When you look at Andromeda with naked eyes, you're seeing light that left there 2.5 million years ago. You're literally looking backward in time, seeing Andromeda as it was when our ancestors were just beginning to use stone tools. The farther you look, the farther back you see, until at the edge of the observable universe, you're seeing galaxies as they appeared just a few 100 million years after the Big Bang. As you drift off to sleep, let these thoughts settle gently. You are made of atoms, forged in stars. You exist on a planet orbiting an ordinary star, in an ordinary galaxy, in a universe containing hundreds of billions of galaxies. Yet somehow, against all odds, matter organized itself into a structure capable of understanding this, of contemplating its own cosmic context, of finding meaning in the vast darkness. Let space remind you that your problems, while real to you, exist in a much larger context. That urgency fades when measured against cosmic time. That beauty persists in the quiet darkness between stars. That mystery remains, no matter how much we learn. Thank you for drifting through space with me tonight. May you rest peacefully beneath the same stars that guided ancient travelers, that inspired countless philosophers, that continue burning patiently in the cosmic dark. Sleep well, and let the thought linger. Somewhere above you, photons from distant stars are streaming earthward. Some will arrive tonight, some will arrive 1,000 years from now, but they're coming, carrying messages from the universe, reminding us that even across impossible distances, even across incomprehensible time, light finds a way to connect us all.